Hey everyone, take a look at your pH, acids, bases, and buffers lab. Now, taking a look at it, on the whole, in my opinion, pretty straightforward. If you've been through the entire sequence at JJC, you've taken Chemistry 100 before taking 101, this is very similar in the first 2/3 of this to that very interesting acids and bases experiment you do with the cabbage juice. Okay, so this is basically a simple experiment involving measuring the pH of various things and equating that to, how much acid or base is present. Okay, so learning objectives, well, there it is. pH measurements compared to calculated values of pH, perform calculations, fundamental concepts of a buffer. Okay, so that's later actually. The first part's pretty straightforward. So one of the first tests you'll do is an electrical conductivity test. Now, if you think about it, seawater conducts electricity really well, right? And this is something you already know. Because it has separate mobile ions in solution, which are called electrolytes, right? So if you have electrolytes in solution, they can move. Movement of charge is electricity, right? And that flows with the push of a voltage, so to speak, okay? So anything that dissociates to make ions will conduct. Now, if you think about it, it's like a big thick wire versus a thin wire. The more ions in solution, the better the conduction. And in our Chemistry 100, we looked at the difference between aluminum chloride, for example, and sodium chloride. And guess what? Sodium chloride puts 2 ions in solution, aluminum chloride puts 4. Aluminum chloride for the same strength, same molarity is 4 ions compared to 2, twice as many ions, twice as conductive. Okay? And if we get into weak acid situations, like maybe it's 10% dissociated, it's a tenth of the conductivity. Okay, so weak acids have a lower conductivity because only a fraction of the molecules make ions. Fully strong electrolytes are more conductive, salts in particular. Okay, so you should see a correlation between electrical conductivity and number of ions in solution. Okay. Now, that's what it talks about here. What does the relative brightness of the bulb mean? More ions. Okay. Now you've got 2 indicators, yeah? So you're going to test the solutions with indicator paper. And if you look at it, so the easy one is phenolphthalein, the one we use all the time in the lab. Okay, so above 8 in basic solution, it's pink. Below 8, it's colorless, yeah? So you just dip it in, you can tell if it's above or below 8, essentially. All right, okay. There's a very slight transitional period, but normally it's a yes or no thing, okay? Similarly, bromo-cresol green, below 4 is kind of yellow, above 4 is kind of blue. So based on the color, you can tell what the pH is, and go from there. All right. So it talks about the correlation between color and pH for indicator paper, okay? So, you do a video, your test materials, and you answer some questions. Pretty straightforward. Okay. Next thing, flashback to Chemistry 100. So, you're looking at the pH of various solutions. Simply Sprite, hint, hint, it's got carbonic acid, right? All carbonated drinks have carbonic acid, should be acidic. Gatorade, mostly sugar water, it's non-carbonated, so it should be close to neutral. Milk, any physiological material is close to neutral. Okay, blood milk, similar, pH 7.2 maybe. Baking soda, be careful. Baking soda is NaHCO3, which basically gives you the carbonate ion, right? And the carbonate ion can pick up H plus to make H2CO3. That's the human body buffer, if you remember that part of the notes, okay? So that's actually going to be picking up H plus, removing H plus from solution to make that, so it's going to be less H plus, more OH minus essentially, right? So that's going to be slightly basic. And then drain cleaner is super basic. It contains, literally drain cleaner contains oftentimes ammonia, but oftentimes chlorate, which is pretty strong base. Okay, all right. You have predicted and observed. Okay. So, you know, if you have pH, you can work out concentration of H plus and concentration of OH minus. So you can use Kw to work those out. Conductivity and pH, relationship between more ions in solution, and if it's acidic, a lower pH, or if it's basic, a higher pH. There's your solutions. Now let's just do a couple by random. Calcium hydroxide is very basic, right? It's a strong base, so we should see a super high pH, and it should be quite conductive. Water now depends, right? Water in the purest state is essentially non-conductive, right? But tap water is conductive because it's like ionic impurities, right? So pure water, super low conductivity, all right? But if it's tap water or salt water, even seawater, it should have a higher. Strong acid, lots of ions, oxalic acid, weak acid. All nitrates are soluble, sodium acetate soluble, sodium carbonate soluble, soluble but a base. So soluble salts, like here and here, should be neutral, right? Because they're not having any kind of strong conjugates in solution. But if I put acetate into solution, that's one of our buffer examples. Acetate, of course, will pick up H+, so that should be slightly basic from a starting point. Strongly basic. Molecules are neutral unless they have natural acid groups. So vitamin C will tell you, does vitamin C have an acidic proton? Yes or no? The pH will tell you that one. Okay. Questions about that? Buffers. Now this is the one where you got to be careful, okay? All right, so for buffers, remember they resist pH changes for addition of H plus or OH minus. We talked about it in the notes, yeah? So remember it's H plus in equilibrium with HA and HA plus A minus. Now, if I add acid to my solution, yeah, okay, it'll move left to reduce it. If I remove acid from my solution by making water by adding OH, right, it'll turn right to make acid, okay? And, you know, it depends on the ratio of A minus to HA, right? If I've got lots of A minus in my buffer, right, so the ratio is 10 to 1, conjugate base A minus to weak acid HA, it will preferentially remove H plus, won't it, right? And that's the way most buffers are. If you remember buffer from the notes, okay? So, you know, it depends on your ratio of these two things, which is better at removing. It will remove both, H plus and OH minus. If you wanted it perfectly in the middle, 50-50 mixture, right? If you wanted to remove H plus, preferentially more conjugate base, and vice versa for OH. Okay. All right, so you're making yourself a classic buffer there, okay? And then you're going to just basically add acids and bases and see what the pH is. Remember, you shouldn't see much of a pH change. Remember, the pH curve looks like that, right? So the pH stays pretty stable over the buffered region. Yeah, okay. And then when you get past the buffered region, it's going to drop or go up quickly. Okay, so you can look at the buffering capacity, right? How far can you go before a big change? Okay, that's pretty much it. Again, read the packets, if you obviously probably already done so, but make sure you understand acid-base equilibria 1 through 3. You understand the questions from the buffer packet regarding buffers. The acetate buffer in the packet will be, and the carbonate buffer will be very, very key for this experiment, okay? So, hope that. Sorry, technical difficulty, my voice control camera. So I think I said, hey, yeah, so any questions, discussion, or water cooler chat, see you guys next time.